Hello, and welcome to Knowledge to Fall Asleep To. Tonight, we're drifting into Earth science, a gentle musical story written not on paper, but in stone, water, air, and time. Listen closely, and you can almost hear it. The slow migration of continents, the endless pulse of the oceans, the patient rise of mountains, lifted, worn down, and lifted again. Beneath your feet, invisible forces press and pull like quiet hands, shaping every coastline you've ever seen, every valley you've ever crossed. Earth science reminds us that this world is never truly still. It is layered, restless, and always becoming, an ancient system that keeps rewriting itself, softly but relentlessly. The ground you walk on carries memories of vanished seas, of glaciers that once ruled the land, of volcanoes that breathed fire into the dark. Rivers remember paths they no longer follow. Rocks hold records older than life itself. Even the air above you belongs to a planet-sized machine that has transformed again and again across deep time. And when you learn to listen, you stop seeing Earth as scenery and start sensing it as a living motion, vast, powerful, and unexpectedly delicate. If you enjoy these calm, drifting journeys, feel free to like, subscribe, or leave a thought below. It helps other tired minds find their way here, one sleepy soul at a time. But for now, you don't need to do anything at all. Relax your body, let your thoughts loosen their grip. Let your eyelids grow heavy. And as the music carries you, we'll explore this fascinating world together. Let's begin. A tsunami can race across an ocean faster than a jet plane. Out in deep water, it isn't a towering wall. It's a long, low swell with a wavelength so vast that ships may barely notice it passing beneath them. Its power comes from the sheer mass of water set in motion over an enormous distance, often triggered by undersea earthquakes, landslides, or collapsing volcanoes. But as the wave approaches shore and the water grows shallow, it slows, its energy compressing upward, turning what looked harmless into a rising force capable of devastating coastlines. Sometimes the first warning isn't the wave itself, but the sea suddenly pulling back, exposing sea floor that is usually hidden. And because tsunamis can arrive in multiple surges, spaced far apart, early warning and evacuation matter. This is ocean-scale energy, transferring its momentum toward land. Long ago, a cataclysmic impact may have formed the moon and reshaped Earth's earliest history. The young solar system was crowded, chaotic, full of growing worlds colliding as gravity sorted the rubble. One leading idea suggests that a Mars-sized body struck the early Earth, releasing unimaginable energy and blasting vaporized rock into orbit. Over time, that debris may have gathered, cooled, and become the moon. If so, it didn't just place a companion in the sky. It likely reworked Earth's surface, stirred its interior, and influenced how the planet cooled. The moon's presence also shapes tides, sculpting coastlines and stirring the oceans. It helps steady Earth's rotation, reducing extreme wobbling over long spans of time. And there's something intimate about that relationship. If the moon formed from Earth's own material mixed with that of an intruder, then the light above you is, in a sense, connected to the ground beneath you. One ancient collision may have set the rhythm of night, oceans, and seasons ever since. Continents move only a few centimeters each year, and it sounds too small to matter, until you imagine it happening year after year across millions of years. Modern GPS stations can measure that slow drift, revealing regions sliding, squeezing, and stretching in real time. When continents collide, neither wants to sink easily, so rock crumples and thickens like a rug pushed against a wall. That is how the Himalayas formed, and why they are still rising as India continues to press northward. Pressure doesn't only build peaks, it bends rock layers, triggers earthquakes, and reroutes rivers. Even after the collision, slow uplift can continue because thickened crust can behave like something buoyant, still pushing upward long after the impact moment has passed. Mountains are not only born in dramatic eruptions, they are also built by patience, measured in motions as small as a fingernail, repeated until the planet itself changes shape. Rivers, too, can change direction when the land tilts and uplift reshapes the slope. Water follows gravity, but the land it crosses is not fixed. If a mountain rises or a region gradually tips, the downhill gradient can weaken, flatten, or even reverse. When that happens, water can be captured by a neighboring drainage system with a steeper pull. Over time, this can carve new valleys, abandon old channels, and carry sediment toward an entirely different coastline. Sometimes the evidence is subtle, a dry valley too wide for the small stream inside it, or a river that makes a sharp, puzzling bend unless its history was rewritten. River capture reveals landscapes as competing systems where basins fight quietly for water, and erosion redraws borders. A river that looks permanent in a photograph may be temporary in deep time, and even its direction can change when geology slowly reshapes the ground beneath it. Most of Earth's volcanoes are hidden underwater, building new crust in darkness. The ocean floor is stitched together by volcanic ridges that wrap around the planet, places where molten rock rises, cools, and becomes basalt. Much of the seafloor is created not by spectacular island eruptions, but along long fractures where tectonic plates pull apart. In some places, seawater seeps into newborn rock, heats up, and blasts back out through hydrothermal vents, forming mineral chimneys that can support ecosystems powered not by sunlight, but by chemistry. Underwater eruptions can look strange. Immense pressure keeps gases dissolved, so lava can ooze into rounded pillow shapes, stacked like dark bubbles, frozen in motion. Because the ocean hides this process, it's easy to forget the planet is constantly rebuilding itself beneath the waves, rewriting maps where almost no one is watching. Some volcanoes don't erupt lava at all, but ice and mud, and they still transform landscapes. In freezing regions and on icy moons, cryovolcanoes can erupt water, slush, or frozen chemicals that flow like slow-motion lava. On Earth, mud volcanoes are another surprise, driven by pressurized fluids and gases forcing their way upward through sediment, often where tectonic forces squeeze the ground or where underground hydrocarbons build pressure. Instead of glowing rivers of lava, you may see fountains of mud, bubbling pools, and sudden flows that bury fields or crack roads. These eruptions can build small cones, open vents overnight, and release methane and other gases into the air. Some persist for years, stacking layer upon layer at a speed that feels almost unnatural for geology. They remind us that geology isn't only about molten rock. It's about pressure-seeking escape and surfaces changing because of it. Volcanic ash can even fertilize the ocean, briefly feeding vast blooms of plankton. Ash is not just dust. It can carry trace nutrients that many waters lack, especially forms of iron needed in tiny amounts by phytoplankton. When winds scatter ash over the sea, those particles can dissolve and become food for microscopic life near the surface. If conditions are right, plankton populations can surge, tinting waters greener and energizing the marine food chain for a time, rippling outward to fish, seabirds, and larger predators that follow the feast. The effect isn't guaranteed. It depends on the ash chemistry, the season, and how the ocean mixes. Still, it's a striking reminder that land and sea are linked. A distant eruption can influence life offshore, not through heat or lava, but through a thin mineral veil falling softly onto water, changing what the ocean can nourish. And dust from deserts can feed forests, carrying nutrients across entire oceans. Desert dust can travel astonishing distances, are lifted high by powerful winds and carried as vast airborne clouds. It isn't just sand, it includes fine mineral particles that may contain vital nutrients like iron and phosphorus. When that dust settles, it can act like a slow delivery system for ecosystems that are nutrient-starved. Some falls into the ocean, helping support microbial life at the base of marine food webs. Some lands on soil, replenishing minerals over long time scales. The journey can span whole ocean basins, linking arid regions to distant rainforests and islands. Dust also leaves traces in ice and sediment, letting scientists track shifting winds and changing dryness through time. What looks like a hazy sky can be part of Earth's nutrient circulation, tiny geological parcels delivered to faraway life. Deep inside Earth, the core is mostly iron, and its motion helps generate the magnetic field. Beneath the crust, a vast outer layer of liquid metal circulates as the planet cools and the inner core slowly grows. Moving conductive fluid generates electric currents, and those currents create a magnetic field in a self-sustaining process called the geodynamo. Earth's rotation helps organize that flow, making a global field rather than chaotic local patches. We can't see the core directly, but its presence is revealed through the behavior of seismic waves and through something as simple as a compass needle obeying an invisible force. The field isn't perfectly stable. It drifts, changes strength, and forms regions of stronger and weaker magnetism across the globe. That deep motion shapes near-Earth space as well, sculpting the magnetosphere, the protective bubble around our world. An ocean of metal at Earth's center makes the sky above safer for life. That magnetic field shields us by deflecting many charged particles from the sun. The sun constantly releases a stream of charged particles called the solar wind, and during bursts of activity, it can hurl far stronger waves of energy outward. Without protection, more of those particles would collide directly with the upper atmosphere, increasing atmospheric loss and raising radiation exposure at the surface. Earth's magnetic field guides much of that flow around the planet and traps some particles in belts surrounding the globe. The shield matters for technology too. Strong solar storms can still cause disruptions, inducing currents that interfere with satellites and power grids, but the magnetic field reduces the overall impact. Mars offers a stark comparison. It has only weak, patchy magnetism, and over time, it lost much of its early atmosphere. Earth's field isn't perfect armor, but it is a powerful filter that helps keep our atmosphere thick and life-friendly. The aurora is space weather made visible, born from Earth's magnetic field. When charged particles are guided along magnetic lines toward the poles, they collide with atoms and molecules in the upper atmosphere. Those impacts excite gases, And as they relax back to normal, they release light in specific colors. Oxygen can glow green or red. Nitrogen can create blue and purple hues. The result is a shifting curtain, beautiful but also informative, reflecting conditions far beyond the clouds. During geomagnetic storms, auroras can spread to lower latitudes, all a sign that the magnetosphere is strongly disturbed. These lights are linked to invisible currents flowing through the upper atmosphere, part of a complex electrical system connecting Sun and Earth. What looks like wonder is also a diagnostic signal, data written in color across the sky, revealing particle energy, magnetic connections, and changes in near-Earth space in real time. A meteorite can contain grains older than Earth, formed before the Sun even existed. Some meteorites hold tiny mineral fragments that did not form in our solar system at all. These pre-solar grains were forged in ancient stars, then blasted into space by stellar winds or supernova explosions. Long before the Sun ignited, that dust drifted through interstellar space, surviving radiation and collisions that could have destroyed more fragile material. When our solar system formed from a collapsing cloud, a small portion of that ancient dust was swept into the growing disk and trapped inside asteroids. Billions of years later, pieces of those asteroids can fall to Earth as meteorites, delivering stardust into human hands. Scientists identify pre-solar grains by unusual isotope patterns, distinct fingerprints of other stellar environments. A rock landing in a field might carry material older than our planet, older than our Sun, older than the very idea of a solar system. Impact craters can also be hidden, erased by forests, oceans, and erosion. A fresh crater is easy to recognize, a bowl with a raised rim and shattered rock. But given time, edges round under rain, rivers cut through rims, and sediment slowly fills the depression. In tropical climates, dense vegetation can mask the shape. Under the sea, water and sediment can bury a crater completely. Some craters are so subtle they're only confirmed when scientists discover unusual rocks, circular patterns, or gravity anomalies hinting at a buried structure. Drill cores can reveal shocked minerals and melt layers that don't form through normal Earth processes. That means Earth has almost certainly been struck more times than our maps can show. The surface is not a perfect memory. It is a self-healing canvas. A crater can exist, cause devastation, and then be slowly hidden until it becomes a secret held inside stone. They are narrow, bottomless cuts in the seafloor, places where one tectonic plate bows, bends, and finally dives beneath another. In some regions, the slope drops so steeply that the column of water above it towers higher than many famous mountains on land. Down there, pressure becomes an unforgiving law. Even a small change in depth can mean a sudden, brutal jump in force. And yet these trenches are not empty. They act like silent collectors, gathering sediments washed from continents over ages, and they shelter highly specialized creatures, life forms engineered by evolution to endure conditions most organisms could never survive. Trenches also sit at the heart of danger because the same subduction zones that carved them can unleash the planet's most powerful earthquakes and the farthest-reaching tsunamis. They are long geological scars across the ocean floor, evidence that Earth is not finished, that it is actively remaking itself. Here, the oceanic crust is flexed downward, and the planet literally swallows part of its own skin. Volcanoes, too, can reach beyond their mountains. The biggest eruptions can cool the climate by loading the high atmosphere with sulfur-rich gases that transform into tiny aerosol droplets, mirrors that bounce sunlight back into space. Unlike ash clouds that fall out quickly, these high-altitude aerosols can linger and spread around the globe, dimming daylight at the surface and lowering average temperatures for a time. That cooling can shift rainfall patterns, stressing crops and ecosystems in different ways depending on the region. A great eruption story isn't written only near the crater. It can be written in strange sunsets, in disrupted seasons, and in the signatures preserved inside tree rings and ice layers. One of the clearest reminders that Earth's climate system responds to sudden shocks, and that the atmosphere can carry that signal far beyond the blast itself. Cold begins as plants, not as rock. Vegetation pressed and buried in waterlogged environments where dead material accumulates faster than it can fully decay. That mass becomes peat, a dark, spongy layer that can thicken over centuries. As more sediment piles on top, pressure and temperature rise, chemistry shifts, water and gases are squeezed out, and the material grows richer in carbon. These seams are more than fuel. They are photographs of vanished wetlands, of forests and swamps that once spread across low basins. Sometimes thin bands of sand or ash interrupt the layers, quiet evidence of floods or distant eruptions that broke the long stillness. And when miners cut into a coal seam, textures and impressions can appear with startling clarity, like a memory preserved from a lost world. It is ancient sunlight stored in the plants, sealed by time, transformed into a concentrated kind of fire. Oil has a different origin story. Ancient organisms, altered by heat within deeply buried sediments. Often it begins with microscopic life from seas and lakes, mixed into fine mud where oxygen is scarce. As burial deepens, temperature rises slowly over immense spans of time, and complex molecules break apart and reorganize into liquid hydrocarbons. The liquid doesn't always stay where it forms. It can migrate through tiny pores and hairline fractures, rising until it meets an impermeable layer that blocks its escape. That is how subterranean traps form, oil gathering in spaces you would never guess exist. Timing is everything. Enough organic matter, enough burial, the right heat, too hot, and the liquid can crack into gas. An oil field is not an underground lake. It's a geological puzzle, chemistry and rock architecture woven together. The oceanic crust is constantly recycled at subduction zones, so it rarely survives for long in geological terms. Continental crust is different, lighter, harder to drag down, capable of enduring repeated cycles of collision and rifting. That's why some continental rocks are astonishingly old, reaching back toward Earth's earliest chapters. Their age isn't a guess. Many contain minerals that locked in radioactive elements when they formed, elements that decay at predictable rates over unimaginable timescales. These rocks have witnessed continents assembling and breaking apart, atmospheres transforming, and life evolving from simple microbes into complex ecosystems. And still, they can be exposed at the surface and weathered by wind and rain like anything else. Stand on an ancient outcrop, and you are standing on deep time made solid. Few experiences make a person quietly humble in quite the same way. Even the air above you has a geological beginning. Earth's earliest atmosphere came from volcanoes, not forests, and it has never stopped changing. The young planet vented gases from within, water vapor, carbon dioxide, nitrogen, and more, while oxygen was scarce. Over long spans, oceans formed as water condensed, and carbon dioxide was drawn down into rocks, reshaping ocean chemistry. Then photosynthetic microbes began releasing oxygen. But the transformation was slow. Oxygen first reacted with iron and other materials, leaving mineral traces of a world adjusting to a new ingredient. Eventually, oxygen accumulated enough to reshape climate, alter seawater chemistry, and open the door for more complex life. The sky is not a fixed backdrop. It is a living result of geology, chemistry, and biology interacting across deep time. Every breath is part of an experiment that is still unfolding. And all of it, trenches, volcanoes, oceans, mountains, returns to the seams between plates. At divergent boundaries, plates pull apart and magma rises, forming new crust that spreads like fresh fabric. At convergent boundaries, plates collide. One may sink beneath another, carving deep ocean trenches, generating massive earthquakes, and building volcanic arcs on land or in island chains. At transform boundaries, plates grind past each other, locking, then releasing in sudden jolts that can shake entire cities. At these seams concentrate change, and they concentrate surprise. Mineral-rich fluids circulate and form ore deposits. Basins develop and may become fertile plains. Coastlines can rise or sink over time. Even the outlines of continents are shaped by where these seams form and how they move. Without plate boundaries, Earth would be quieter, but it would also be flatter with fewer mountains, less nutrient recycling, and a very different surface for life. Some volcanoes don't even need a plate boundary. Hotspots, long-lived sources of heat rising from deep within Earth, can punch through moving plates and leave trails of volcanoes behind. The plate keeps moving, so the volcanoes don't stay above the hot spot. A new one forms. The older one is carried away. And over time, a chain of islands or seamounts can stretch for thousands of kilometers, like a wake behind a ship. Except the ship is a tectonic plate, and the wake is built from volcanoes. As the older volcanoes drift away, they erode and subside. Coral reefs may grow into rings that later become atolls. Hotspots help explain volcanoes far from plate edges and provide a rare way to measure plate motion using geological footprints across the ocean. Hawaii is a slow-motion compass, recording movement as each island and underwater mountain grows older along the chain. The dramatic bend in that chain isn't just a map oddity. It hints that plate motion itself can reorganize over deep time. Earth is layered like an onion, and the deep interior remains partly mysterious. We live on a thin crust, but beneath it, the mantle holds most of the planet's volume, hot enough to flow slowly while remaining solid rock. Deeper still lies a liquid outer core and a solid inner core under crushing pressure. We know this without drilling down there because we listen to seismic waves. They bend, speed up, slow down, and sometimes vanish depending on what they pass through. That's how scientists discovered a liquid layer that blocks certain wave types completely. Even now, details are debated: how fast the inner core rotates, how rough the core mantle boundary is, yet these hidden layers shape volcanoes, drive plate motions, and help generate the magnetic field that shields the planet. That magnetic field can flip. When lava cools, tiny iron-rich minerals inside it can align with the field like microscopic compass needles, frozen in place. Over time, those fixed directions build a library of past magnetic behavior on the seafloor. New crust forms at mid-ocean ridges, carrying the field's current signature, then moves outward, creating symmetrical stripes on both sides. Those stripes helped prove seafloor spreading, and they reveal that reversals are irregular. Sometimes the field stays stable for tens of millions of years. Sometimes it flips more often. A reversal isn't a simple switch. The field can weaken, tilt, and grow complex before stabilizing again. Life continues, but the sky's invisible shield changes shape. Earthquakes can even make the ground behave like liquid. In loose, water-saturated sediments, often near rivers, bays, or reclaimed land, shaking can cause grains to rearrange and water pressure between them to rise. Suddenly, friction fails, cohesion vanishes, and the ground flows. Buildings can tilt as if the surface has softened. Buried tanks can pop up like corks. Streets can crack and spit fountains of sand and water, small eruptions called sand boils. Liquefaction isn't soil melting. It's a structure collapsing in a terrifyingly short moment, which is why engineers care so deeply about soil type, drainage, and groundwater depth. The same earthquake can be survivable on solid bedrock and catastrophic on saturated ground. Even a single grain of sand can tell a story about mountains that no longer exist. Sand isn't just tiny rocks. It's evidence, clues about origin and the journey. Under a microscope, geologists can see whether grains are sharp or rounded, hinting at transport by wind, river, or waves. They can identify minerals like fingerprints. Some grains contain a zircon, a crystal tough enough to survive intense weathering while preserving the age of the rock it came from. By dating zircons in modern rivers, scientists can trace sediments back to ancient sources, even when the original mountains have been worn down to low hills. Beaches, dunes, and deltas become archives of landscapes that vanished, detective work written in dust, water carves too, but in different voices. Rivers concentrate energy into narrow channels, especially when land rises or sea level drops, and they cut down through rock, leaving steep walls and winding bends that follow weaknesses in cliffs. Glaciers work differently. Slow-moving ice masses dragging stones like sandpaper across bedrock. Instead of narrow cuts, they widen and deepen entire valleys, carving broad U-shaped cross-sections and leaving hanging tributary valleys high above. Glaciers can pluck blocks from the ground, carry debris for miles, and pile it into ridges called moraines. A river's signature is sinuous and sharp. A glacier's is wide, polished, and dramatic. Both obey gravity, but they reshape the planet at very different tempos, one roaring in floods, the other transforming whole regions while seeming almost still, then vanishing and leaving its sculpture behind. Earth's crust itself comes in two flavors: buoyant continental crust and denser oceanic crust. Continental crust is thicker and floats higher, often made of silica-rich rocks with lighter elements. Oceanic crust is thinner, denser, and largely born from mantle melting. This simple contrast explains much of the planet's shape. Continents ride high like thick logs, while ocean basins sit low because heavier crust sinks deeper. Where these meet, the boundary can become a rugged seismic zone. Coastal mountain ranges, offshore trenches, and unstable slopes. Chemistry matters to daily life too, because weathered continental rocks become soils that feed forests and farms. The next time you look at a world map, you're really seeing two kinds of crust arranged into a surface that never stops changing. And the ocean floor, for all its vastness, is not permanent. It forms, cools, drifts away from the ridge, gathers sediments, sinks as it cools, and eventually reaches a destructive end, bending down and disappearing into Earth again. That conveyor belt keeps the seafloor geologically young compared to continents. It also means the seafloor is a moving archive, recording ocean chemistry and sediments, carrying heat that shapes currents and ecosystems, yet always destined to be rewritten. Pages torn from the book almost as soon as they are written. Subduction zones can even drag water deep into Earth, changing rocks far below. Some water sits in sediments and pore spaces beneath the seafloor. Some is locked inside minerals formed where seawater reacts with hot rock and becomes part of a crystal structure. When a plate sinks, pressure and heat squeeze these hydrated minerals, releasing water that rises into the overlying crust. That water lowers rock's melting point, helping generate magma that fuels volcanic arcs. It also drives strange transformations inside the sinking slab, forming dense, high-pressure minerals that could never exist near the surface. This is one reason subduction zones can produce both devastating earthquakes and brand new crust. Deep recycling, with water acting as a catalyst, carrying a surface ingredient into depths it was never meant to reach. The longest mountain chain on Earth isn't a famous skyline at all. It's the mid-ocean ridge system, an immense, winding range of peaks and valleys running through the Atlantic, Pacific, Indian Ocean, and beyond. In many places it rises like a broad underwater plateau, split by a rift where new crust forms. The rock there is still warm, so the seafloor is lifted. As crust moves away, it cools, contracts, and sinks, helping create the deep basins that hold the oceans. In some sections, offsets and fractures step the ridge into terraces. The ridge is also a heat engine. Seawater circulates through cracks, warms and returns, altering ocean chemistry over long time scales. The longest mountain range on Earth is real. Most of it simply lies hidden beneath kilometers of water. After massive eruptions, a caldera can form, not just a crater blasted out, but a collapse. When a large magma reservoir empties enough, the ground above loses support and sinks, sometimes in stages, creating a broad depression with steep inner walls. These collapses can reshape entire regions in an instant by geological standards. Later, the basin may fill with a lake, build new domes, or host smaller eruptions that rebuild parts of the floor. Calderas can also power geothermal systems as hot water circulates through fractured rock. The peaceful beauty of a caldera lake can hide an origin story of violence, and the basin itself becomes a reminder of how much empty space can open beneath the ground before the surface finally gives way. Beneath the deep ocean, basalt rules. Dark rock, born from lava that cools quickly. When molten rock meets cold seawater, it chills so fast that crystals stay tiny, giving basalt a fine, smooth texture despite its glowing liquid past. Underwater, lava often piles into rounded pillow shapes as if the melt swelled and froze mid-motion. On land, basalt can spread in vast flood lavas, building step-like plateaus and weathering into fertile soils. Basalt is also a traveler. As oceanic crust moves away from ridges, seawater circulates through cracks and chemically alters it, adding minerals and changing its composition. In that way, a simple black rock becomes part of a long dialogue between ocean and interior. Granite tells the opposite story. Slow formation, deep underground, crystals large enough to see. It begins as magma trapped within the crust, insulated by surrounding rock, cooling gradually. That slow cooling gives minerals time to grow, creating a mosaic of interlocking crystals, glassy quartz, pale feldspar, darker specks of mica or hornblende. Granite often forms far below volcanoes, meaning it spends most of its life hidden. It reaches the surface only after uplift and erosion peel away the layers above, like a sculpture revealed by subtraction. In places with huge batholiths, granite builds towering cliffs because it is strong and fractures in dramatic patterns. Every visible crystal is a record of time spent cooling in darkness, Earth taking its time to finish a stone. Obsidian is volcanic glass, lava cooled so fast it never had time to become stone in the usual way. Instead of orderly crystals forming and locking into place, the melt freezes mid-motion, trapping atoms in a chaotic arrangement, like a liquid caught in a sudden still frame. The result can be dark and smoky, sometimes streaked with a sheen that looks almost wet when strong light hits it. When obsidian breaks, it doesn't crumble like ordinary rock. It fractures in smooth, curved arcs and produces edges so sharp they feel unnatural, sharper than you'd expect from something born of fire. That razor quality made it priceless to many cultures for blades and tools. And even today, it still finds specialized uses where extreme sharpness matters. But obsidian isn't just useful, it's informative. Tiny gas bubbles can be sealed inside it, and subtle chemical signatures can point to the specific eruption that forged it. By matching that chemical fingerprint, archaeologists can trace obsidian traded across vast distances, turning a single stone blade into a map of ancient connections and human movement. It is fire that cooled too quickly to become rock the normal way. And that is exactly what makes it extraordinary. Pumice tells the opposite kind of volcanic story, not glassy and dense, but riddled with trapped air. It forms when gas-rich lava erupts, and pressure drops so suddenly that dissolved gases explode outward into foam. The molten material stretches into a froth and hardens before the bubbles can escape. That frozen foam leaves pumice full of holes, so many that it can feel almost weightless, and in some cases, it can even float on water. After major eruptions, pale volcanic debris can blanket landscapes and pour into the sea. Out there, pumice fragments can drift for months, sometimes gathering into rafts that ride ocean currents across entire basins. Those floating fields can carry hitchhikers, barnacles, algae, and other clinging life, creating moving stepping stones that help organisms spread into new places. Eventually, water seeps into the pores, the stones grow heavy, and the voyage ends as the raft sinks. It's a quiet reminder that even solid rock can behave like a boat if it is born under the right volcanic conditions. Metamorphic rock is shaped by pressure and heat without fully melting, a transformation by force, not by fire. Imagine a rock buried so deep that temperatures rise, pressures clamp down, and minerals become unstable. Instead of turning to liquid, the rock changes in place. Crystals dissolve and regrow. Minerals reorganize into new forms. The texture can shift so completely, it's as if the rock has learned a new language, rewritten from the inside out. This happens during mountain building, when layers are shoved downward and sideways over immense spans of time. It also happens near intrusions, where heat radiates slowly into surrounding rock like a long, patient kiln. Metamorphism can harden rock into something tougher, or it can create plains of weakness that later guide landslides and erosion. It can turn dull sediments into slate or transform basalt into dense green rock packed with newly formed minerals. And sometimes, in the most beautiful twist of all, it grows gemstones, brilliant accidents born from crushing pressure and deep time. Marble begins as limestone, often built from shells and chemical deposits in ancient seas. That means marble is a transformed memory of ocean life and ocean chemistry. When buried and heated, the original calcite grains recrystallize into a tight mosaic of interlocking crystals that can take an extraordinary polish. That's why marble can seem to glow, as if light slips a little way inside before returning. Impurities add drama. Iron can blush it pink or red, graphite can smudge it gray, and other minerals paint green veins and swirling patterns like frozen motion. Marble also reacts to weak acids, which is why acid rain can soften carved details over time. That fragility is part of its paradox, precious and vulnerable at once. In a single slab, you can hold a story that starts in warm, shallow seas, passes through burial and mountain making, and returns to the surface as a stone human shape into art. Some rocks sparkle because their minerals have been forced into alignment. Deep underground, pressure can become directional, stronger from one side than another. Under that squeeze, platy minerals like mica rotate and grow in a shared orientation, like countless thin pages stacked the same way. When the rock is exposed and split, those aligned surfaces catch light and flash silver. Schist often forms in the heart of mountain belts where rock is compressed, heated, and stretched in collisions. It can contain garnets that grow like tiny time capsules, their chemistry changing as they expand, quiet witnesses to the conditions of metamorphism. And then there are the rocks with bold bands, geology painted into stripes. Those layers aren't decoration. They're the result of minerals separating during intense metamorphism, with lighter minerals gathering into pale bands and darker minerals concentrating into dark ones. A rock may begin as granite or layered sediments, then be altered so profoundly that its internal ingredients reorganize. Sometimes partial melting heightens the contrast, producing patterns so striking they resemble wood grain. These banded rocks often appear in the ancient cores of continents, regions rebuilt again and again through collisions. When you see them at the surface, you're often looking at deep crust lifted into daylight, a window into Earth's interior architecture. Sandstone can preserve ripples, ancient shorelines frozen in rock. Ripple patterns form in minutes as water or wind moves grains into repeating ridges. If that surface is buried quickly, it can be protected, later cemented into stone, and survive for millions of years with the clarity of fresh footprints. Sandstone can also hold cross-bedding, tilted layers left behind by migrating dunes or river bars. Those angled structures reveal flow direction, wind patterns, and whether the environment was beach, desert, or river channel. Some sandstones even preserve mud cracks, evidence that the ground was once wet, then baked dry under sunlight. With these clues, geologists can rebuild vanished landscapes with astonishing precision. Sandstone isn't just rock. It's motion, preserved by burial and time. Mud can become shale, then slate, and beyond, an entire journey from softness to strength. It begins in calm water, where the finest particles settle slowly, forming thin layers that can record seasons, storms, and changes on surrounding land. As more sediment piles on, pressure squeezes water out and compacts the mud into shale, which splits along its original bedding. If that shale is later caught in mountain building, pressure can rearrange its minerals and create slate, splitting along a new direction called cleavage. With higher heat and pressure, the rock becomes increasingly transformed, sometimes brittle, sometimes shattered, sometimes suddenly beautiful, until what was once seabed mud can become the core of a mountain. That's the deeper truth. The rock cycle isn't a neat loop, it's a tangled network. A rock might start as melt, cool into solid stone, rise and weather into fragments, settle into layers, harden into sedimentary rock, then be buried and reshaped into metamorphic material, maybe even melt again to feed a volcano and return to the surface in a new identity. Some rocks never melt, some never settle, some are altered by hot fluids without extreme heat or burial. Earth loves detours, shortcuts, and dead ends. The rock cycle is less like a circle and more like a city map. Countless intersections where the planet chooses what happens next. Minerals themselves form like recipes, structures assembled from elements under specific conditions. Change the temperature, pressure, water, or oxygen, and you don't get the same crystal. Oh, you get a different mineral, different hardness, different color, different shape. Slow cooling deep underground can grow large, well-formed crystals. Rapid cooling near the surface can create tiny grains, or freeze melt into glass with no crystals at all. Some minerals form only where seawater reacts with fresh oceanic crust. Others require the violence of mountain building. Each mineral is a clue because it can only exist within a narrow range of conditions, like a recipe that fails if the oven is too hot. Quartz is one of the great survivors. It's hard, resistant to chemical attack and physical abrasion, so it endures while weaker minerals break down into clays or vanish. Over time, wind and water grind rocks into sand, and quartz remains, persistent, stubborn, unchanged. That's why so many beaches sparkle with durable pale grains. A quartz can travel immense distances down rivers, tumble in surf, and still keep its identity. In deserts, it can gather into vast moving seas of dunes. In other places, quartz-rich sands harden into sandstone and later rise into cliffs and arches. One mineral can appear as a clear crystal, a beach of grains, or a towering wall, reused by landscapes again and again without losing its name. Feldspar is equally common, but it plays a quieter, world-shaping role. It weathers into clay. Water and weak acids seep into tiny cracks, and feldspar slowly reacts, transforming into clay minerals. The change is gradual, but its consequences are enormous. Clay helps soil hold water and nutrients, supporting plant growth and shaping ecosystems. It also changes how land behaves in rain, making slopes slicker, increasing landslide risk, and turning roads into mud. In rivers, clay can stay suspended for a long time, clouding floodwaters and carrying fine material far downstream. Over long spans, clay-rich layers can compact into shale, preserving delicate laminations that whisper of still ancient waters. Feldspar doesn't simply disappear. It becomes the foundation of fertile soil, river mud, and entire sedimentary basins. Chemistry, turning into landscape. Iron-bearing minerals can rust, too, painting cliffs red over time. When these minerals meet oxygen and water, they oxidize into new compounds that are often red, brown, or yellow. The same basic process that reddens old metal, but on a geological canvas. Gray rock can warm along cracks where water seeps. Fresh landslide scars may start pale, then darken as oxidation progresses. In deserts and canyons, the iron oxides can cement sediments into harder layers, helping some strata resist erosion and stand out as ledges. Iron staining can also reveal hidden patterns, tracing ancient pathways where fluids once moved underground. Rock color isn't just decoration. It can be evidence of exposure, moisture, and chemical change. A landscape can shift hues without changing shape, as if Earth is slowly repainting the same scene. And sometimes, the smallest crystals carry the oldest memories. Zircon is tiny, but famous for surviving almost everything, formed in hot magma, then eroded, transported, buried, even metamorphosed, often without being destroyed. Inside its crystal lattice, zircon can lock and trace elements and tiny impurities, preserving clues about the environment where it first grew. Some zircons found in younger rocks are far older than the layers that contain them because they were recycled from ancient crust. Geological heirlooms passed from one era to another. The oldest known zircons reach back toward Earth's earliest history, hinting at conditions when the planet was still young. Hold a grain like that, and you're holding a survivor that crossed nearly unimaginable time. Proof that the deepest past is sometimes stored in the smallest places. Caves keep secrets with a patience the open world can't match. Outside, wind and rain constantly remix the record. Inside, the air moves slowly. The light barely reaches, and information can rest undisturbed for ages. Stepping into a cave can feel like stepping into silence. But for scientists, it can feel like stepping into a preserved sample of an earlier atmosphere, a sealed room in Earth's long memory. Glaciers and ice sheets do something even more astonishing. They archive the breath of the past as bubbles trapped in ice. Fresh snow falls fluffy and full of empty space. As more snow piles on, its own weight compresses the layers below. The snow becomes firm, denser, still porous, until little by little the pores close. In that moment, tiny pockets of air are sealed off forever, locked into solid ice like insects in amber. Those bubbles aren't nothing. They are time capsules of ancient sky, captured at the instant the ice became airtight. By extracting and analyzing those gases, scientists can measure past levels of carbon dioxide and methane and compare them with temperature signals preserved in the ice itself. That pairing is what makes ice so powerful. It's a double archive of climate and of air running in parallel, and the fidelity is haunting. Air that last touched the world tens of thousands of years ago can still be measured with precision, molecule by molecule. A glacier is not merely frozen water, it is a library shelving breaths from vanished worlds. Ice cores read like stacked diaries. In places where snowfall accumulates without melting, each year can leave a distinct layer, brighter or darker, depending on seasons, dust, chemistry, and storm patterns. Drill deep enough, and you pull up a vertical timeline you can hold in your hands. Volcanic eruptions appear as spikes of ash and sulfate because distant blasts sprinkle their fingerprints onto the ice. Shifts in wind patterns show up as changing dust. Ocean influence leaves traces of sea salt. Even temperature can be inferred from the chemistry of water molecules because isotopes subtly shift with cold and warmth. The beauty of an ice core is that it doesn't depend on stories being told correctly. It depends on snow falling, freezing, and staying frozen. Once that layered structure is set, it becomes a timeline of winters and summers stacked in order, waiting to be translated. And yet, glaciers are not always gentle. Most creep forward so slowly they seem still, but some suddenly surge, lurching ahead at 10 times their usual speed or more. The trigger can vary. Meltwater can lubricate the base. Internal deformation can reorganize the flow, or soft sediment beneath the ice can turn into a slippery layer that lets the whole mass slide. During a surge, ice can thicken to fracture into chaotic folds and bulldoze debris forward. Downstream, valleys can clog, and lakes can form behind temporary ice dams. The strangest part is the rhythm. Decades of calm, then a brief burst of violent motion, then calm again, like a slow machine that occasionally jerks awake. Surges are a reminder that ice is not a passive remnant of cold. It can be an active force that reshapes landscapes on human timescales. Glaciers also leave signatures at their edges, ridges of rubble called moraines, written in stone like a boundary line. Ice is rarely clean. It plucks rock from valley walls and grinds material from the bed beneath, carrying that debris like a moving conveyor belt. When the glacier pauses or retreats, it drops that load, building ridges that mark where the ice once stood. Some moraines look sharp and fresh. Others have been softened by time and vegetation. Either way, they are positions in a glacier's past, frozen into the terrain. Hikers can walk along these stony ridgelines without realizing they're tracing the outline of an ancient river of ice. Landscape art made by glaciers using rock as ink. The last ice age redrew coastlines, and the sea's later rise erased whole worlds. When ice sheets expanded across continents, they stored so much water that global sea level fell dramatically. Shorelines shifted outward, exposing broad coastal plains where shallow seas used to be. Humans and animals could cross land that is now underwater, and river systems carved valleys into the exposed continental shelves. Then the climate warmed, the ice melted, water returned to the ocean. Shorelines marched inland again, drowning river valleys into bays, reshaping continental edges, flooding lowlands built from thousands of years of sediment. Today's coasts are not ancient boundaries, they are snapshots, carved by ice, meltwater, and time. Stand on a beach and you're standing on a line that has wandered back and forth across the map, guided by how much water the planet hides in ice. Even after the ice disappears, the Earth keeps reacting. A thick ice sheet presses the crust downward, not because the crust is weak, but because the mantle beneath can slowly flow over long time scales. When the ice melts, that weight is removed and the land begins to rebound. The rise is slow, millimeters per year, but it can continue for thousands of years. This uplift changes local sea level even if the ocean itself doesn't move. Old beaches can end up stranded high above the water as raised terraces. Harbors can become shallower, wetlands can shift. A coastline can change shape without any earthquake or tectonic collision at all. The landscape is still recovering from an ancient burden, like a body slowly straightening after carrying a massive load. Fjords are one of the most dramatic receipts of glacial power. Drowned glacial valleys, carved deep and then flooded by the sea. They begin as workshops of moving ice. A glacier flows through a valley, grinding bedrock, widening and deepening the channel, ripping blocks from the walls. Because ice can erode below sea level, fjord basins can become startlingly deep, often deeper than the nearby ocean. When the glacier retreats and the sea pours in, the result is a long inlet with steep walls rising straight from dark water. And many fjords also have a shallow sill near the mouth built from debris or shaped by erosion that influences circulation, traps deeper water, and affects marine life. Fjords aren't just beautiful. They're proof that ice can sculpt rock on a colossal scale, then hand the finished basin to the ocean like a completed masterpiece. And glaciers don't only carve, they grind. That grinding can create loess, fine wind-blown silt that builds fertile lands far from its source. Loess can look like simple dust, yet it can accumulate into thick blankets across whole regions. Often it begins with glaciers pulverizing rock into flour-fine particles. Rivers spread that sediment onto dry plains. Then wind lifts it and carries it, sometimes hundreds of kilometers, before it settles in layers. Loess can stand in steep, near vertical cliffs because its grains interlock with surprising strength. Over time, it weathers into rich, productive soil, which is why many agricultural heartlands sit atop loess plains. Its fertility comes from minerals, water-holding ability, and a structure roots can easily penetrate. Loess is proof that landscapes can be connected by airborne pathways, that a glacier can help feed distant fields not only through rivers, but through wind. Weathering and erosion are partners, but they aren't the same. Weathering breaks rock down in place, chemically and physically. Water dissolves minerals. Oxygen oxidizes iron. Acids from soil alter crystals into clay. These changes weaken the material from the inside out. Erosion is the removal, the carrying away by rivers, wind, ice, and gravity. A landscape can be heavily weathered, yet barely eroded if the broken material stays put. Or it can be strongly eroded with little chemical change if physical removal dominates. Together, they form the sediment supply chain that builds beaches, deltas, and seafloor layers, while also carving valleys and exposing fresh surfaces. One process prepares, the other executes. In cold climates, freeze-thaw cycles act like a relentless wedge. Water seeps into a crack. Temperature drops. The water freezes and expands, forcing the crack open a little wider. When it warms, more water enters. Then it freezes again. Over many cycles, solid rock can split into blocks and angular debris, building talus piles at cliff bases and priming slopes for rockfalls. This isn't a single dramatic blow. It's a slow lever applied again and again, often more effective than any one storm. The chisel isn't a tool. It's water-changing state. Life joins the work. Roots can widen cracks, turning biology into a slow geological force. A seed lands in a fissure, sprouts, and pushes into spaces you'd barely notice. As the root thickens, it applies steady pressure, especially as moisture changes make it swell and shrink. This isn't just destruction. It's the beginning of soil. Wider cracks invite more water, more chemical weathering, more organic matter. In some landscapes, roots stabilize slopes by binding loose material. In others, they help pry cliffs apart. Lichens and microbes add their own influence, producing acids that chemically roughen rock surfaces and prepare them for physical breakup. Living things don't merely occupy geology. They participate in shaping it. Soil, in the end, is not dirt. It's a living system made of minerals, microbes, water, air, and time. Weathered rock provides the raw grains, but biology gives soil its character. Microbes break down dead organic matter, recycle nutrients, and create compounds that glue particles into stable aggregates. Fungi extend networks that move water and nutrients through the ground. Roots pump sugars into the soil to feed communities that, in return, can protect roots from disease or improve access to phosphorus and other nutrients. Soil structure matters as much as chemistry. Good structure lets water infiltrate, reduces erosion, and helps roots breathe. Healthy soil stores carbon, filters pollutants, and softens floods by absorbing rain. It also keeps a history. Layers can preserve traces of vegetation, fire, and land use. When soil is lost, it isn't quickly replaced because its formation depends on slow interactions among rock, climate, and life. It is the planet's living skin. A teaspoon of healthy soil can hold billions of microorganisms, bacteria, fungi, archaea, tiny predators, an underground metropolis of chemical conversations. Some fix nitrogen from the air into forms plants can use. Some produce natural antibiotics that shape which species thrive. Around roots in the rhizosphere, microbes respond to plant signals and sugars and in return can boost nutrient uptake or defend against pathogens. This hidden world also affects climate because microbes control how fast carbon is released from decaying matter or stored in more stable forms. Two soils only a few steps apart can host different microbial communities shaped by moisture, vegetation, and history. When you hold soil, you're not holding something dead. You're holding an ecosystem performing chemistry under your feet at the speed of life. Then come the sudden rewrites. Earthquakes can trigger landslides that reshape valleys in minutes. Shaking destabilizes slopes, and gravity suddenly wins. Yesterday's intact hillside can become a moving mass. Some slides are shallow and fast, stripping soil and trees like a rough broom. Others collapse into huge blocks, leaving fresh scarps and tilted ground behind. The most dangerous can dam rivers, creating temporary lakes that may fail and unleash floods downstream with little warning. In mountain regions, earthquake-driven rockfalls can bury roads and reroute rivers in a single event. And the cracked slopes can remain unstable for years, ready to be reactivated by the next storm. An earthquake isn't only shaking, it can be a sudden redesign of slopes, rivers, and terrain. Not all faults announce themselves with violence. Some slip quietly, slowly enough that GPS can measure it, or a painted line on pavement can reveal the shift. Instead of locking and snapping, certain segments creep a little at a time. The movement can bend rails, crack walls, and deform the ground without producing the strong shaking people associated with earthquakes. Slow slip can happen where fault rocks contain slippery minerals or where fluids reduce friction at depth. It matters for hazard planning because a creeping segment may relieve stress locally while transferring stress to a locked segment nearby. It also gives scientists a rare chance to study a fault in motion. Not only in the aftermath of disaster, a fault that creeps is still alive. It's simply choosing a quieter language. Liquefaction adds another twist. Buildings can tilt even when they aren't structurally broken. In strong earthquakes, water-saturated ground can lose strength and behave more like a fluid than a solid foundation. A building might not crack apart, yet it can settle unevenly as the ground shifts beneath it, one corner sinking, another lifting, until the whole structure leans. Roads can slump. Buried pipes can rise to the surface. Bridge approaches can lose support. This is common in young river deposits, reclaimed coastal land, and loose fills where groundwater sits near the surface. The damage can be subtle but severe. Walls look intact, but doors won't close and floors are slanted. Engineers reduce risk by densifying soil, lowering groundwater or transferring loads to deeper, stable layers with piles. The unsettling lesson is that a building can survive the shaking and still be betrayed by the ground itself. Seismic waves, meanwhile, let us see inside Earth without drilling, like an ultrasound for a planet. An earthquake sends vibrations through the globe. They speed up, slow down, bend, and sometimes vanish depending on what they travel through. Some waves pass through solids and liquids. Others cannot cross liquids at all. By comparing arrival times at many stations, scientists map variations in velocity that reveal hot regions, cold slabs sinking into the mantle, and the boundaries between major layers. That's how we inferred the size of the core and confirmed the existence of a liquid outer core. Modern seismic imaging can even show remnants of ancient tectonic plates deep below, fossils of vanished oceans, and unexpected features like partially molten zones or unusually complex mantle structures. The planet is continuously scanned for free by every earthquake. Each quake becomes a signal source. Each seismometer becomes an ear pressed to the ground. Deep below, the mantle circulates slowly, driven by heat inside Earth, pushing tectonic plates from beneath. The mantle is mostly solid rock, yet over long distances and long times it can flow because pressure and temperature allow minerals to deform. Hot material rises. Cold, dense material sinks. The circulation pulls plates apart at mid-ocean ridges and drags them down at subduction zones, linking deep interior motion to surface geography. Sometimes, a sinking cold slab behaves like a heavy curtain, tugging the rest of the plate behind it. Elsewhere, rising mantle thins the crust and encourages rifting. The speed is imperceptible in a lifetime, but over millions of years, it rearranges continents, opens oceans, raises mountains, turning deep heat into surface change through the slow engine of the planet. Some natural gases, however, don't come from volcanoes. Tektites form when an impact is so violent it melts surface rock and flings droplets high into the atmosphere. Those droplets spin, cool, and solidify into glassy objects that can fall far from the crater, scattered across vast, strewn fields. Their shapes often look aerodynamic because they were still soft while flying through air. Their surfaces can be etched and pitted by heating and ablation. Unlike volcanic glass, tektites typically contain very little water, reflecting their extreme formation and rapid cooling. Finding one can feel like discovering a message mailed across a continent by a single ancient moment. Dark pebbles that traveled through fire, sky, and sudden return. All of this sits inside deep time measured in billions of years, far beyond everyday intuition. Human lives are decades, written history is centuries. Earth's story is told in spans so vast they bend the mind. Eons contain eras, periods, and epochs, names chosen not for drama, but because rocks change character across those boundaries. Chemistry shifts, fossils appear or vanish. Sediments tell a different environmental story. Once you start thinking in deep time, mountains look temporary. Coastlines look recent. Entire oceans can open and close. What feels permanent is often just the current frame of colossal film. Mass extinctions are some of the film's sharpest cuts. Ecosystems reset, and geology keeps the receipts. In a mass extinction, many species vanish in a short geological moment, and survivors inherit a changed planet. Forests shift. Oceans reorganize. Food webs rebuild from scratch. The clues aren't only fossils, They're also in abrupt carbon isotope shifts, ash-rich layers, black shales that hint at low oxygen seas, evidence of widespread wildfire, signs of rapid warming or acidification. Afterward, rock records often show a new kind of ecosystem emerging, different dominant groups, new strategies for survival. These events are tragic, but also coldly creative. They open ecological space and accelerate evolutionary experiments. Geology preserves the ledger, layer by layer, showing how catastrophe can become a turning point. The end Permian extinction, the largest known, left global chemical scars. Rocks across the world show sharp disruptions in the carbon cycle, widespread oxygen loss in the oceans, and collapsing ecosystems on land as forests thinned and food chains broke. One leading suspect is immense volcanism in what is now Siberia, releasing enormous gases that could have driven warming, acid rain, and ocean changes. Details are still debated, but the evidence points to a planet pushed hard and fast, followed by a slow recovery where simpler ecosystems persisted for a long time before diversity returned. What makes it unsettling is the scale, not a local disaster, but a global crisis etched into stone across continents. Ocean anoxia, loss of oxygen, can spread, suffocating marine life and changing sediment itself. Oceans don't always mix evenly. Under certain climates and circulation patterns, deep waters can lose oxygen faster than it is replenished. As oxygen drops, decomposition changes, and organic matter can accumulate in dark carbon-rich muds, later forming widespread black shales. Many animals cannot survive these conditions, especially those trapped in deeper basins. Chemistry shifts too. Elements behave differently in oxygen-rich water than in oxygen-poor water, so sediments record the transition like a signature. These events aren't just tragedies for sea life, they are reorganizations of how the ocean works, written into rock as a warning and a memory. Music can shape the long, quiet machinery of the planet, how carbon is stored, how nutrients cycle, how climate steadies itself across centuries. It's a reminder that ocean health depends on circulation, not just on life. The sea surface may look calm, but the deep can turn harsh and oxygen poor, rewriting ecosystems from below, the way a slow fever changes a body long before the face shows it. Coral reefs leave behind a different kind of memory, limestone that records sea level like a stone tide gauge. Reefs grow close to the sunlit surface, so they live at the edge of the waterline. If sea level rises slowly, coral can build upward and keep pace. If it rises too fast or drops too far, reefs drown or are exposed, and their growth patterns shift. Over long spans of time, those shifts become architecture in rock, stacked layers, terraces, repeated growth surfaces, even step-like platforms that mark pauses and reversals, like tick marks on a ruler. Because reefs are widespread and can be dated, they let scientists compare sea level change across regions. And their limestones can also preserve storm debris and wave energy signatures, adding detail to the story of migrating coastlines. A reef is not only a habitat, it is coastal engineering built to match the waterline. When the sea moves, the reef responds, and the stone remembers. Coral fossils can also reveal ancient ocean temperatures through chemistry. As corals build their skeletons from calcium carbonate, they incorporate tiny variations in isotopes and trace elements that depend on water conditions. Those variations act like a thermometer written into the skeleton itself. Many corals even show seasonal bands, like growth rings, recording the pulse of warming and cooling within a single year. That makes corals unusually persuasive. They offer direct evidence of past ocean conditions, not just indirect hints. From fossil coral, scientists can reconstruct currents, climate swings, and the history of warm and cold periods, and learn how sensitive reefs are to environmental change, which matters for what comes next. A coral fossil isn't just a pretty pattern in stone. It's a data record made by a living creature, written in chemistry, while it fought to survive at the border between sea and sky. Beneath that border, the ocean runs on moving rivers, currents driven by temperature and salinity. Warm water expands and tends to rise. Colder, saltier water grows denser and sinks. That density difference powers a planet-wide conveyor, carrying heat from the tropics toward higher latitudes, then returning cold water to the deep. Where winds push surface water away from coast, deep water can upwell to replace it, delivering nutrients that feed fisheries. Currents steer storms and shape regional climates because the ocean stores heat far more efficiently than air. Even oxygen depends on circulation because mixing ventilates deeper layers. When currents strengthen, weaken, or shift, coastlines can feel it through changes in fog, rainfall, and sea ice. The currents are Earth's moving climate control system, and they never truly stop. On the seafloor, hydrothermal vents build mineral chimneys like underwater factories. Seawater seeps into cracks, sinks, heats near hot rock, then rises again carrying dissolved metals and minerals. When that superheated fluid hits cold seawater, the dissolved material can precipitate instantly, forming tall chimneys and flanges dark of sculptural towers that grow, collapse, and regrow in months or years, fast by geological standards. These fluids can also alter the surrounding rock, leaving distinctive mineral zones that mark where circulation once flowed. They are natural reactors moving heat and chemistry through Earth's crust, assembling architecture from seawater and stone. And life thrives there without sunlight, powered by chemical energy. Many vent animals live in partnership with microbes that turn vent chemicals into usable fuel. Giant tube worms are famous for it. They lack a typical digestive system and instead house dense bacterial communities in specialized tissue. Their blood carries unusual molecules that can safely transport both oxygen and sulfide, feeding their microbial partners without poisoning the worm itself. Clams and mussels do similar things. Shrimp graze on microbial films coating rocks. Growth can be rapid because chemical fuel can be steady and strong. But vents are scattered and temporary, so life must disperse when an old vent shuts down. The result is a network of biological outposts across the deep sea floor, connected by drifting larvae, shaped by the rise and fall of the vents themselves. Methane seeps create another strange refuge, ecosystems fed by gas leaking from below. In some regions, methane rises through sediments from deep reservoirs or from methane hydrates locked in cold layers. Where methane meets seawater chemistry, microbes can consume it, often in reactions involving sulfate. Those reactions can change the seafloor dramatically. Carbonate minerals precipitate, forming hard crusts and rock slabs on what was once soft mud. Those carbonate platforms become habitat, shelter for sponges, corals, and many other animals. Some seep communities include clams and tube worms that also rely on microbial partners. but the seep environment often feels different from vents. Cooler, gentler, slower. Methane seeps matter for the carbon cycle too, because microbial consumption can prevent some methane from ever reaching the water column and atmosphere. A seep is like a slow leak from Earth's pantry, enough to gather a whole community around it. Now the sediments themselves are taking on a new signature. Microplastics have been found from beaches to deep-sea mud, and the tiniest fragments can settle like sand grains into accumulating layers. Over time, those layers may become distinct, synthetic polymers mixed with shells and clay. Future geologists could identify them by chemistry, shape, and even the additives used in manufacturing. Microplastics can also concentrate pollutants, changing how chemicals move through bottom ecosystems. In quiet basins where sediment builds steadily, the signal could become startlingly clear, a thin, persistent marker of recent human activity. Unlike a surface stain that fades, a buried layer can last, compact, and eventually lithify into rock. In that sense, microplastics are not only litter, they are potential stratigraphy, a durable fingerprint of the industrial age, filed into the same archive that preserves ancient ash and prehistoric shells. Humans have also created new rocks at global scale, especially concrete. It binds sand and gravel with cement, and cement is made by heating limestone and other materials until they react into new compounds. Mixed with water, it hardens into stone-like mass that can last decades or longer. As cities spread, concrete becomes an artificial geological layer. Foundations, roads, seawalls, bridges. Over time it can crack, weather, and be buried, forming future strata containing rebar, glass, brick, and other manufactured debris. Techno-fossils with distinct signatures and datable traits. Concrete even interacts with the carbon cycle. Cement production releases carbon dioxide, while old concrete can slowly reabsorb some CO2 through weathering. Either way, it's a sign that human activity is now shaping the planet's surface in ways that could be recorded in the geological record. The built environment can even bend local weather. Cities replace vegetation with dark roofs, asphalt, and concrete that absorb sunlight and store heat. That warmth can lift air, triggering convection, especially when moisture is present. Cities also add pollutants, tiny particles from traffic, industry, and construction that can influence cloud formation and droplet growth. The results can be complex. In some conditions, certain cities experience heavier rainfall, often downwind, where rise in air and cloud physics line up. Lightning frequency can shift as storms pass over warm urban cores. At night, cities cool more slowly than surrounding countryside, prolonging local winds and temperature contrasts. Weather isn't only sculpted by oceans and mountains. It can be nudged by the geometry and heat of what we build. The skyline can quietly reshape the sky. Even underground, time is stored. Some groundwater is not part of a fast local cycle. It can be ancient water that infiltrated during past climates when rainfall and temperature were very different. In arid regions, modern recharge can be so limited that pumped water is essentially a relic of older, wetter eras. Scientists can estimate its age using dissolved gases and isotopes, timestamps that reveal when the water last touched the atmosphere. Ancient groundwater can be remarkably pure, filtered through rock for thousands of years, or it can pick up minerals that make it salty or enriched in certain elements. Some aquifers are confined beneath sealing layers that hold pressure, creating artesian wells that flow without pumping when tapped. The idea is both comforting and unsettling. Beneath a desert, there can be water that fell as rain when the land was grassland and lakes. Once it's gone, it may not return on any human timescale. Aquifers can also collapse when overdrawn, causing land subsidence. An aquifer isn't an underground lake. It's water stored in pore spaces within sediment and rock. Remove too much water, pressure drops, grains compact, and in soft sediments, that compaction can be permanent. Even if water later returns, the storage capacity may be lost. On the surface, subsidence appears as slow sinking that cracks canals, tilts buildings, and increases flood risk. Along coasts, it can worsen storm surge and let tides reach farther inland. It can also encourage saltwater intrusion because reduced freshwater pressure allows seawater to push into aquifers. Subsidence often happens unevenly, creating hidden stresses that damage infrastructure in unexpected places. Groundwater is a resource, but it's also structural support. Take too much, and the ground itself can settle, turning an invisible depletion into a visible change in the landscape. Lakes have their own breathing cycles. In many temperate lakes, summer warmth makes surface water lighter, so it floats above colder, denser deep water. This stratification keeps deep water in darkness, where oxygen is gradually consumed and nutrients build up. In autumn, the surface cools, the density difference weakens, and wind can mix the entire lake from top to bottom. That turnover pushes oxygen down into depths that have been depleted for months, and it lifts nutrients towards sunlight, fueling new blooms of algae and microbes. In spring, a similar mixing often happens after ice out, as surface water warms back through the same temperature range. These seasonal pulses shape fish habitat, water clarity, even the smell of a lake after a windy day. The surface can look still, but inside the lake is breathing to its own rhythm. Sometimes chemistry announces itself in shocking color. Acid mine drainage shows how reactions can turn streams bright orange. When sulfide-rich rock is exposed during mining, it can react with oxygen and water to form sulfuric acid. That acid dissolves metals, carrying them into nearby streams. When acidic water mixes with cleaner water and meets oxygen, iron can precipitate as rusty orange coatings over rocks and stream beds. The color can look unreal, like the water has been painted. But the damage isn't cosmetic. Acidity stresses aquatic life, and dissolved metals can be toxic even when water looks clear. The small mercy is that the process is predictable, which makes monitoring and treatment possible. Adding alkaline material to neutralize acid or using constructed wetlands to promote metal-removing reactions. It's a lesson in unintended consequences. Digging into earth can change chemistry far beyond the mine itself, reshaping whole watersheds downstream. Other waters build stone instead of staining it. Natural springs can deposit travertine, layer by layer, forming terraces over centuries. Some groundwater dissolves limestone underground and brings dissolved carbonate to the surface. When the water emerges, it releases carbon dioxide into the air, and that shift causes calcium carbonate to precipitate as solid rock. Over time, it forms rimmed pools, step-like terraces, smooth cascades that look sculpted but are built by chemistry. The textures can be delicate, ripples, leaves, even branches can be coated and preserved. Colors often come from trace minerals or microbial mats thriving in the flowing water. These landscapes also record change. If flow shifts or weakens, construction patterns shift too, leaving abandoned terraces like old staircases. Travertine is geology on human scale, slow enough to what? Fast enough to reshape a hillside within a lifetime. Geysers are rarer still because they require a very particular plumbing system, one that mineral deposition can eventually choke. A geyser isn't just hot water. It's a delicate balance of heat, water supply, and underground passages that can hold pressure. Water seeps down, heats near hot rock, becomes superheated under the weight of water above. And if the plumbing has constrictions, bubbles can accumulate until pressure suddenly releases, blasting water and steam upward. Most hot springs don't have the right geometry for that dramatic cycling, and the plumbing is fragile. Minerals can precipitate and slowly coat the channels, changing their shape. Small earthquakes can open new cracks or seal old ones. Even changes in groundwater level can alter timing. A geyser field is a living laboratory, gaining vents, losing vents, changing rhythm without warning. When a geyser goes quiet, it often means the underground system has silently rewritten itself. Permafrost carries one of the biggest quiet stores of carbon, and thaw can open the door. In cold regions, ground can stay frozen for years, even millennia, locking away plant material that microbes couldn't fully decompose in the cold. All that preserves vast amounts of carbon. When permafrost thaws, the ground can become waterlogged and unstable. Microbes wake up and begin breaking down stored organic matter, releasing carbon dioxide in oxygen-rich conditions and methane in wet, oxygen-poor conditions. Thaw can also reshape land quickly. Ground slumps, lakes form, coastlines erode faster when the ice that once bound sediments disappears. This matters because it links climate and geology in a feedback loop. Warming thaws, permafrost. Thaw releases greenhouse gases which can amplify warming. Permafrost isn't just frozen soil. It's a long-term carbon vault. And thaw is the door beginning to swing open. Volcanic landscapes show the planet's double nature, danger in the short term, abundance in the long term. Fresh ash and lava fragments can weather into mineral-rich soils loaded with potassium, calcium, and magnesium. Over time, rain and biology break the material down into fine particles that hold water and nutrients, creating dark, fertile soils that can support lush forests and productive farms. One reason many agricultural regions sit near active or recently active volcanoes. The trade-off is risk. The same volcano can deliver ash fall, lahars, or lava flows that threaten communities. Volcanic soils can be stable and erosion-resistant in some places, and landslide-prone on steep slopes and heavy rain elsewhere. They're a balance of renewal and hazard, depending on the time frame you choose. All of these threads tie back into the carbon cycle, a planet-wide accounting system that moves carbon through rock, ocean, air, and life. Carbon isn't only in the atmosphere. Plants pull CO2 from air and pass it into soils and food webs. In the ocean, carbon dissolves. Organisms use it to build shells. Shells become sediment. Sediment becomes carbonate rock. On land, weathering can draw CO2 into chemical reactions, eventually delivering carbonate ions to the sea. Deep underground, subduction carries carbon-bearing rocks into the mantle, and volcanism can return CO2 to the sky. Some of this cycling happens in days through leaves and microbes. Some stays locked in limestone for millions of years. The carbon cycle links climate to geology and explains why Earth's temperature can shift over long time scales, as carbon moves between reservoirs that seem separate but are tightly connected. Even minerals can remember temperature. Certain minerals form and change in ways that depend on heat, and their chemistry can preserve that information long after the heat is gone. In metamorphic rocks, minerals appear in sequences as conditions evolve, each with stability ranges that act like clues. Some crystals hold subtle zoning, different compositions from core to rim, recording changing conditions as they grew. In other cases, mineral pairs exchange elements until they reach a temperature-dependent equilibrium that can be measured later. That allows geologists to estimate how hot rocks became during mountain building or deep burial, and even infer how quickly rocks rose back toward the surface, because rapid uplift can freeze mineral patterns before they fully re-equilibrate. The wonder is simple and profound. Rock can remember temperature. A hand-sized sample can hold a heat history no human witnessed, yet careful measurement can reconstruct it in the silent language of chemistry. Earth science, in the end, is the study of connections. It's tempting to treat landscapes, weather, and ecosystems as separate subjects, but they are threads of the same fabric. Mountains influence rain by lifting air, creating wet forests on one side and dry deserts on the other. Rivers carry eroded sediment to coasts, building deltas and feeding wetlands that protect shorelines. Oceans store and release heat through currents, shaping storms and seasons on land. Soil bridges living and non-living worlds, made from rock, powered by microbes and roots. Hazards reveal the links too. Earthquakes trigger landslides that dam rivers. Climate change shifts snow cover and flood timing. Once you notice these connections, the planet stops looking like a set of separate scenes. It starts to look like an interacting system, always adjusting, always responding. And the landscape itself is not finished. A canyon wall looks eternal, but it's a single frame in a long process. Rivers keep cutting, slopes keep slipping, rock keeps turning into sediment, then becoming rock again somewhere else. Coasts migrate as waves sort sand and as land rises or sinks. Forests expand and retreat with climate. Soil thickens or thins depending on how fast rock weathers and how fast erosion removes it. If you could speed up time, hills would move like slow waves and shorelines would walk across maps. The art of earth science is learning to read that motion in the present. So, as this journey winds down, the planet may feel more alive than it did at the start. Beneath each step are stacked layers like history books and patient engines moving stone. Coastlines shift, valleys widen, mountains rise, then surrender, grain by grain. Even the quiet seafloor is busy, creating new crust, carving deep trenches, raising mineral towers in darkness. Above it all, air and water keep circulating, carrying heat, salt, dust, and nutrients, stitching distant places together. And while we listen, Earth keeps doing what it has always done. Rivers swell and where their banks, waves sort sand. The magnetic field stretches into space. The planet moves without hurry, yet never stops moving, changing in its own time. Now let those ideas settle. Picture a wide horizon at sunset, the last warmth held in stone, the sky open and calm. Slow your breathing, to drop your shoulders, Let your thoughts drift like clouds that don't need to decide where they're going. If an image of a glacier, a canyon, or a deep ocean trench rises in your mind, let it pass gently, like a quiet postcard from a vast world. If you enjoyed this slow walk through earth science, you can support the channel by liking, subscribing, or leaving your thoughts below. And if you're still awake, there's another video waiting on your screen, ready to carry you onward. For now, rest is enough. Good night and sleep well.